Hello all, I'm back with another past paper walkthrough video. So I see, and it makes me really happy, I see more and more comments coming into my videos from people who find the past paper walkthroughs very useful for them. And I promise to make new videos, but the problem is that I haven't solved all the past papers myself, and therefore I cannot upload new videos very frequently. However, I went through my folder with past papers that I have from the time I was teaching, and I found this paper from January 2018. Now, the problem with this paper is that it's from the past, the previous spec, okay? As you can see, it does say Unit 4, but then it says Physics on the Move. Now, this has changed in the new spec to, I think, oscillations, nuclear physics, something like that, okay? So the spec has changed, but it didn't change dramatically. I mean, most of the things that we will go through in this paper are very similar to the things that you need to know in the current spec. So we will just go through this paper, and whenever there is a question that is irrelevant to the current spec, I will indicate that, okay? So let's go. I mean, if I don't say anything, it means that a problem is relevant for the current spec as well. So let's start. Okay, section A, question 1. Some of Rutherford's alpha scattering experiments used radium as a source of alpha particles. Which of the following nuclei will be produced by alpha emission from radium 226, and then the proton number is 88. So first of all, we can work it out. So this guy will emit an alpha particle, right? And to balance the equation, we will need a new element, let's call it Y, which will have 222 protons and neutrons and 86 protons, right? Because on the right hand side, 86 plus 2 makes 88, and 222 plus 4 makes 226. Okay, let's read off these elements. We see that the only correct option is C. Okay, now let's move to question 2. Which of the following is not a lepton? Okay, the electron and the neutrinos the electrons and neutrinos are leptons, and so are positrons. A pion is a meson, so C. Question 3. A capacitor of capacitance C stores a charge Q when the potential difference across it is V. Which of the following expressions is the energy stored in the capacitor? So the answer is, okay, let me check my notes. This is problem 4. And the something is wrong in my notes, is it? No. So the option is D, okay. I'm sorry for the hesitation. Now, since this is an old spec, I want to go to the back of the paper and see the formulas they give you. Okay, so Unit 1, Unit 2, Unit 4. Okay, so let me see. Mechanics, fields. Yes, energy stored in a capacitor. So that's the one I was looking to find. Okay, so let's go back to question 3. So 1/2 QV is what they give you. So to recover option D, you have to use C is equal to Q over V, which means that V is Q over C. And if you combine these two, you get 1/2 Q times Q over C, which is Q squared over 2C, which is option D. So that's the proof. Question 4. The photograph shows the track of a positron in a particle detector. There is a magnetic field perpendicular to the plane of the track. Which of the following is not a correct statement? A. The energy of the positron is decreasing. That's true because, as you can see, it spirals. Let me use a different color. so it spirals inwards, which means that it's losing energy. Okay, the magnetic field acts into the page. So again, we need to use Fleming's left-hand rule to verify this. So if it's into the page, the magnetic field points inwards, which means that we have to put our index finger to point into the page, right? And then the direction of motion of the positron is to the right, and we know this because it spirals inwards and it's losing energy as it spirals. Okay, so if we put our middle finger in the direction of the velocity, we see that the force is upwards, and that's true actually, right? Because that's the centripetal force that makes this spiral motion possible for the positron. Okay, see, the positron is gaining mass. No, because it's actually losing energy. That for that we will need the positron to speed up. Okay, so C is not correct, and then let's just read off D. The speed of the positron is decreasing. That's the case actually, right? Because as it spirals, it loses energy. So actually, if you want to be accurate, let me erase everything. So the velocity vector for circular motion is tangent to the motion, right? So if this is the initial velocity, this vector will gradually become smaller and smaller, okay? And the reason for that is that it's losing energy, okay? So let's move on. Question 5. The potential difference across a charged capacitor is V naught. The capacitor discharges through a fixed resistor. After a time equal to the time constant, the potential difference has reduced to V. Which of the following is a correct expression for V? So let's read it again. So after a time equal to the time constant. Okay, so in general, V is equal to V naught e to the minus t, where t, the English t, or the Latin t, is the time elapsed, and tau is the time constant, okay? So if the time t is equal to the time constant, then we will have V naught e to the minus tau over tau, which deletes itself. So this is equal to V naught over E. So the answer is B. Okay. So far, the only comment I have to make, I can make, because I haven't seen this since, I think I went through these past papers back in 2023 when I used to teach at the high school. It looks easier, okay? I mean, the previous spec looks easier than the current one. But anyway, let's keep moving. Baryons and mesons are types of particles that consist of quarks. Which row of the table shows a possible quark combination for a baryon and a meson? Okay, first of all, this row and this row are totally wrong because they show a meson with 3 quarks, so that's totally wrong. And then we can also cross out option B, and the reason is that I'm sorry. And the reason is that the meson needs to have an antiquark. Okay, so the only option that makes sense here is D. Okay, because a baryon has to have 3 quarks or 3 antiquarks, and a meson has to have 1 quark and 1 antiquark. All right. Question 7. Which of the following is a unit of the permittivity of free space E naught? Okay, this is okay. No. This is I was thinking that maybe this is a question that is related to the previous spec, but it's a valid question for this for the current spec in 2026. So let's do it. So K, the constant, the Coulomb's constant, is 1 over 4 pi epsilon naught. Okay, that's the way to work this out. So E naught is 1 over 4 pi K. Now, For those of you who have never watched videos of mine, I use these square brackets to denote the units that go with some physical quantity, okay? So E naught is 1 over 4 pi, which is unitless, okay? And then 1 over the units of k. So this is simply 1 over the units of k. The units of k now are 1 over newtons, coulombs to the minus 2 meters squared. So this is equal to coulomb squared meters to the minus 2 newtons to the minus 1, which is option D. How did I know that the units for k are these ones? You can use Coulomb's law, okay? So let me use a clean page to show you. So Coulomb's law tells you that the force experienced between two charges, say, is K Q1, Q2 over R squared, right? So the units of F will be equal to the units for K, and then the units for Q1, units for Q2, and then units for R squared. The units for force are newtons. The units for K are what we are looking to find. The units for Q is coulomb, and we have 2 of them, so coulomb squared over meter squared. So the units for K would be newtons, meter squares, coulombs to the minus 2. Okay? So the units for E naught will be 1 over that, pretty much. Okay. Question 8 now. The following circuit is used to charge a capacitor. Which of the following pairs of graphs shows the variation of the current I in the resistor with time t and the variation of charge Q stored in the capacitor with t? Okay, so when we close the switch, a current runs through this circuit, okay? So that's the current. So the current I in the resistor, in the beginning, the current will be maximum, right? But as charge starts to build up on the capacitor, initially the capacitor will start with 0 charge, okay? As charge builds up in the capacitor, the current reduces until it goes to 0. Okay, so we need to find a graph for current that is exponentially decreasing. So the only options are A and B. Okay, but in option A, they show the charge in the capacitor decreasing from a maximum, but the capacitor is discharged when the switch is open, right? So the correct answer is B. Okay, and in the modern spec, they actually expect you to know the equations for the charging of a capacitor, okay? So for discharging, let me use a clean page. Okay, so for charging of a capacitor, Q is Q naught e to the minus t over tau. For, sorry, this is discharging. Sorry, discharging. Okay, for charging now, the equation is Q is equal to Q naught times 1 minus e to the minus t over tau. Okay, so for discharging, the equation looks like it's an exponential decay like that. So discharging, but for charging, this is the form of the equation of the graph. Okay, so this is for charging. Moving on to question 9. Okay, immediately I sense that this is a trick question. So 2 charged spheres of equal mass, okay, are suspended with insulating threads of equal length. One sphere has a charge of plus q and the other has a charge of plus 10q. Which of the following shows the arrangement of these spheres when they are in equilibrium? Okay, so take a moment to think about it. It's really easy, but tricky. Okay. Okay, now you're probably back from pausing the video, and the correct answer is C. Okay, and the reason for this, okay, is that is Newton's third law, right? So when an object exerts a force on another object, okay, the other object exerts the same force in the opposite direction on the first object. Okay, so we have two objects and two different charges, but the force they exert on each other is equal. Okay, so they will be in equilibrium like that. Okay, because one charge is going to be pushing, so there will be two forces like that pretty much. Okay, and there is nothing more to say, I think, so let's move on. Question 10. A student is investigating how the magnetic flux through a coil varies with its angle in radians to a magnetic field. Okay. Which of the following gives the equivalent angle in radians for an angle of 40 degrees? Oh, so this is, okay, the actual question is this one. I don't know why they mentioned the first part. So, which of the following gives the equivalent angle in radians for an angle of 40 degrees? So 40 degrees times pi over 180 degrees, pretty much. Do they have an option like that? No, they don't, but they have this one. Okay, so this is also equal to 40 degrees times 2 pi over 360 degrees. So B is the correct answer. All right, so as you can see, so far, all the questions in part, in section A are possible questions that you can see in the modern spec. So let's move on to question 11, which is the first question in section B. Okay, we are back with section B. I'm saying we are back because I'm filming the second part in a different day than the first part, okay? And I'm filming this in my car because, okay, I'm not homeless yet. I do have a place to stay, but it's not ideal to filming videos. So I will try to complete this test and upload it from my car, okay? So I have a feeling that my handwriting will get worse because it's not comfortable to write in the arrangement I have right now in front of me. The good news is that next to me is the sea, okay? So I have a really nice view. You cannot see that, but anyway, let's get started with question 11. Okay, so a K0 particle decays producing a pion, a muon, and a neutrino. Complete the nuclear equation to show the charges on the particles. Okay, so we have zero charge in the left-hand side, so you have to have zero charge in the right-hand side. So it can be a plus and a minus, or a minus and a plus. How can we tell which one is which? We have a muon antineutrino. Muon antineutrinos have a lepton number of -1, okay? And negative muons, okay, have a lepton number of 1. So 1 minus 1 is 0, okay? So we have a 0 lepton number on the right-hand side, just like the left-hand side, because the left-hand side is just a pion, sorry, a meson, okay? And mesons don't have lepton numbers. Okay, so if the muon has a minus charge, then the pion needs to be a positive pion, okay? And that's the answer. Hope this makes sense. Part B now says ordinary matter is made up of protons, neutrons, and electrons. At the time they were discovered, these particles were not thought to be made up of any other particles. So in the beginning, when these particles were discovered, people thought that these particles were fundamental, okay? Now the question is, explain how the proton, neutron, and electron are described in the current standard model of matter. Okay, so let's start with the electron, for which we know that it's a lepton, okay, and it's a fundamental particle. Okay, I warn you that my handwriting is going to take a hit because it's difficult to record. using the steering wheel of my car pretty much to rest my iPad on. So it's kind of difficult, okay? Now the proton consists of 3 quarks, U, U, and D, okay? Let me try to make a better D. There you go. And it's a baryon number. Sorry, it's a it's a baryon in the standard model. And U has a charge of 2/3, and D has a charge of minus 1/3. So 2 times 2/3 makes 4/3, minus 1/3 makes 1. Okay, and then the neutron consists of a U and 2 Ds. Okay, quarks, and it's also a baryon. Okay, and maybe you can write that the charge is 0. Okay, and maybe you can write here that the charge is 1 and the charge here is minus 1. Okay, Q is minus 1. Okay, question 12. The diagrams below, okay, represent the path of an electron in a vacuum. Okay. Okay, so in the diagram 1, we see that there is no magnetic field, and there is some potential difference across the plates. And in diagram 2, there is magnetic field into the page and no electric field. Okay, and we see that in the second diagram, the electron does not make it out of the plates. Okay, using both fields at the same time, it is possible to balance the forces so that the path of the electron is not deviated. Okay, for such an electron, its velocity v is given by that equation. Okay, where v is the potential difference across the plates, d is the separation of the plates, and b is the magnetic flux density. Show that this equation is correct. Okay, so to balance the electron, we need the total sum of all forces to be 0. Okay, so it goes in a straight line. What are the forces the electron experiences when it passes through an electric field? Q. Let's call it force due to the electric field. Okay, that's given by Q times E. And for parallel plates are a special case in which the electric field is given by the voltage over the distance between the 2 plates. Okay, so that's a good start. And this is diagram 1. Diagram 1. Then for the second diagram, don't know what happened. Okay, sorry. For the second diagram, the force due to the magnetic field is Q times the velocity of the electron times the magnetic field. Okay, so that's diagram B. So we pretty much have to have these 2 forces balancing. Let me use a clean page. So we need force E, the force due to the electric field, to be equal to the force due to the magnetic field, or Q times V over D to be equal to Q. Okay, let me write the voltage like that to distinguish with velocity, which I write also with V. Okay, so that's supposed to be a lowercase v, and that's supposed to be an uppercase. This is supposed to be an uppercase v, but okay. And we need the magnetic field density. Okay, so Q cancels, so V needs to be equal to V, the voltage, over D times the magnetic field. Okay, is this the same as what they ask us to find? Yes. Okay, and let's move on. Question 13. In the 1920s, Patrick Blackett, maybe? Okay, I don't know how that's pronounced, but anyway, he investigated the interaction of alpha particles with different atomic nuclei. Okay, So the diagram shows an alpha particle interacting with a stationary nitrogen nucleus. Wait a second, I'm confused. Okay, so it shows okay, they show us, so that's the alpha part, oops, let me use red. So that's the alpha particle, and the alpha particle gets scattered, and then you have a nitrogen nucleus that goes like that. Okay, and they show us this arrangement in this diagram over there. Okay, now it makes sense. All right, so let's erase this line. Okay, the alpha particle rebounded off the nitrogen nucleus. The nitrogen nucleus recoiled in the other direction. Okay, the directions of the paths are shown in the diagram. Cool. The initial speed of the alpha particle was 1.2 times 10 to the 7 meters per second, and the speed of the alpha particle after the interaction was 6.93 times 10 to the 6 meters per second. They give you the mass of the alpha particle as 4 atomic mass units, and the mass of nitrogen nucleus as 14 atomic mass units. And a rule of thumb, if they ask you to actually calculate this, so the rule of thumb is that if you have carbon 12, okay, its mass is 12U. If you have nitrogen 14, its mass is 14U, and so on and so forth. So you multiply the mass number with atomic mass units, okay? In general, that's not accurate. In actual precision measurements, maybe the mass of nitrogen 14 is 14.0023 atomic mass units or something like that, okay? But just to have an order of magnitude in your head, like when you want to make an estimation. So, question A showed that the speed of the nitrogen nucleus after the interaction was about 5.2 times 10 to the 6 meters per second. Okay, so they give us the velocity of the alpha particle before and after. Okay, so okay, let me see how I want to do this. So if we go back to this diagram, okay, we can resolve the vectors. So, and I'm talking about the velocity vector. Okay, so the easiest will be to use, so we have to conserve momentum in the x and y directions, right? So what's the y component of the speed of the alpha particle? It's, let's call it v a sine 30 degrees, okay? And what's the final velocity of nitrogen? Okay, actually, let's draw it like this. And for nitrogen, the y component of the velocity, and therefore the momentum, I mean, we can actually, the momentum analyzes the same way as the velocity. So here that's the y component of the momentum of the alpha particle. So if we multiply with ma, we have the momentum in the y direction, and the momentum in the y direction for the nitrogen will be m, let's call it n, times vn times sine of 10.9 degrees, okay? And these two components need to be equal to each other. So this is what we will use, and hopefully we know everything. We know the masses, we know the velocity of the alpha particle after the collision. So we need to find the velocity of the nitrogen, right? So this should work. Let's see. So ma va sine 30 should be equal to the mass of nitrogen, velocity of nitrogen, sine of 10.9 degrees. So if we solve for Vn, we find ma, let's do it like this, ma va sine 30, and then in the denominator we have mn times sine of 10.9 degrees. So if we plug in the values, we have 4u times 6.93 times 10 to the 6 times 0.5, which is the sine of 30 degrees. And in the denominator, we have 14u times 0.1891, which is the sine of 10.9 degrees. So u cancels, and we find 5. Oops, I told you my handwriting is going to take a toll in the arrangement I'm using today, which is my car. Okay, so 5.23 times 10 to the 6 meters per second, which is exactly, not exactly, I mean they ask for 5.2, so yeah, we got it. Now part B, determine whether this this interaction was elastic. Okay, so we need to find 1/2 ma times ua squared. Okay, we have to calculate that. Ua is the initial speed of the alpha particle, and okay, we have to make that squared. And the final energy, kinetic energy of this system is 1/2 the mass of the alpha particle times its final velocity squared. The final velocity is the one we used up there, okay, and plus 1/2 mn times vn squared, okay, and vn is the velocity we just found. Okay, let's calculate the top, which is the kinetic energy before. That's equal to 2 atomic mass units times 1.2 times 10 to the 7 squared. Okay, and 1u, I think is 1.66 times 10 to the negative 27 kilograms. This is off the top of my head. Let's actually check this just to make sure. Okay, so yes, unified atomic mass unit, yes, so I'm right. Let's go back. Let's go back. Okay, here, right. Okay, and so this is equal to 4.78 times 10 to the negative 13 joules. And if we calculate the quantity on the bottom, we will find 4.77 times 10 to the negative 14 joules. So the interaction is indeed elastic, right? So the interaction is elastic. All right. So far, so good. Let's move on to question 14. As you can see, all the questions so far, even though we are working with a really old spec, it's 8 years old by now. I mean, time flies, right? But even the old spec is, I mean, the questions are similar to the new spec. So, okay, that gives us confidence to keep moving. Okay, now let's work on question 14. When an X-ray photon interacts with an atomic nucleus, pair production can occur. In pair production, the photon energy produces an electron and a positron. For this to occur, the wavelength of the X-ray photon must be less than a certain value. Show that the maximum wavelength of the X-ray photon is about 1 times 10 to the negative 12 meters, which is 1 picometer, right? Or 1000 nanometers. So, no, what did I say? Is 1000 nanometers? No, 1/1000 nanometers. I'm sorry. So, anyway, so we have to use our beloved Uncle Albert's formula. So, delta E is delta mc squared because energy and mass are equivalent. Okay, and now for the energy, we will use the energy of the photon that we want to uncover. So H times C over lambda should be equal to delta m c squared, right? So let's solve for lambda. So this means that the energy of the photon will turn into the mass of the two particles. Okay, so lambda should be equal to h times c over delta m c squared. So c cancels. And by the way, c over lambda is f, right? Because f is c over lambda. And the energy of the photon is, of course, h times the frequency. Okay, so let's plug in numbers. And by the way, delta m is the mass of two electrons, right? Because the electron and the positron have the same mass. So let's plug in numbers. Actually, just to make sure I'm not confusing you, I'm going to write this down. Delta m is 2 me c squared. Okay, now let's plug in numbers. So 6.63 times 10 to the negative 34 joules seconds. And then, wait, it's not c squared, it's c. We cancelled one of the c's, remember? Sorry. So 2 times 9.11 times 10 to the negative 31 is the mass of an electron, and then this is in kilograms. And then c is 3 times 10 to the 8 meters per second. Okay, so I'm gonna work these units in the back. Okay, so this is 1.21 times 10 to the negative 12 meters if you use your calculator. And how do I know that it's meters? Actually, there is space here, so let me work the units. A joule is 1 kilogram. 1 joule is 1 kilograms times meter squared over second squared. How do I know that? Because 1/2 mv squared is the kinetic energy that has units of joules. So joules is equal to, so actually let's write it down. I ran out of space, so let me move this there. So kinetic energy is 1/2 mv squared, which means that a joule, which is the unit for kinetic energy, is equal to kilograms meter squared over second squared. Okay, the units for, I mean, you don't need the 1/2, right? Because that's a dimensionless quantity, it's a pure number. So 1 joule is 1 kilogram times meter squared over second squared, and then we have the second squared, and then we have the meters and the kilograms. So kilograms cancel, second squared cancels, and we are left with meters in the numerator. And we found value very close to the one we are asked to find, so we are good. Let's move on. State why 2 electrons cannot be produced by pair production, because that would violate conservation of charge. Okay, because that reaction would be, we can write it like gamma goes to 2 electrons, so we have a charge of 0 going into a charge of -2, which is forbidden. So I'm going to put that cross there. So this is not possible. Okay. After production, the positron and the electron move off in different directions. Suggest what happens to the electron and the positron after this. So this is a trick question. So you have to get a little bit creative. So what will happen to the electron? The electron is a matter particle, okay? So it interacts with regular matter, so it will lose energy. So the electron will lose energy through ionization, whereas the positron is an antimatter particle. So the moment it will encounter a matter particle or an electron, it will annihilate, right? So positron, so the positron, I'm sorry, will annihilate with another electron. And that's the answer. Now, let's move on to question 15. So the diagram represents a toy aeroplane, on the end of a string. Okay, that looks good. The toy aeroplane follows a horizontal path of radius r, and the string is at an angle theta to the vertical. Complete a free body force diagram for the toy aeroplane. Ignore any forces due to the air. So I guess it flies in a circle that goes around like this. Okay, so let's put the forces. So you have, by the way, I forgot that if I hold my pen, it makes the lines straight and nice. So, okay. Okay. And this. No, this is not what I need. I'm sorry. Let's go back to what we had. So this is what the aeroplane does. So now let's put the forces. Here we do need a straight line. No, it's not the straight line I want. I actually want the straight line to be this way. Okay. Okay. So that's the tension from the string. Okay. And the other force is simply the weight. Okay. M times G. These are the only forces on the plane. Right. Question 2. The toy aeroplane completes 36 revolutions in 1 minute. So whenever we see something like this, revolutions in 1 minute means 36 revolutions per 1 minute, which is 60 seconds. So that's a frequency. Calculate the speed of the aeroplane. Okay, so V, and they give us the radius, which we will need. So the linear velocity, oops, I want the black. So the linear velocity is omega times the radius, right? And omega is 2 pi times the frequency times the radius. And now we have 2 pi times the frequency is 36 over 60, right? Because we have 36 revolutions per 60 seconds. So 1 over seconds is hertz, so that's the frequency. And then times, 2 pi times the frequency times 0.4 meters, which is the radius, and final answer is 1.5 meters per second. Part 3. By considering the vertical and horizontal components of tension, show that the angle theta is independent of the mass of the toy aeroplane. All right, so let's go to the diagram here. So, okay, let me draw the vertical component. Okay, that's, so if I come here and draw the vertical component, so this is the tension, and this is the weight, right? So if this angle is theta, this is also theta by Thales principle. So that component is T cosine theta, and this component is T sine theta, which is the centripetal force. So that's theta, T cosine theta, and T sine theta. Okay, so T sine theta, as we just said, is the centripetal force. So it's equal to m omega squared. Something's wrong in my notes, by the way. I just realized. So m omega squared times r. And now I'm doubting myself, so I'm going to check the marks, sorry, the equations back here. Yeah, m omega squared times r. So something's wrong in my notes over there. I don't know why I made that mistake. So anyway, let's go back. T sine theta is m omega squared times r, and then t cosine theta balances the weight, because if it didn't, we will have an upward motion, which we are told that we don't have. So t cosine theta is m times g. Now, if we divide these equations, we get tangent of theta, the masses cancel nicely, is equal to omega squared times r over g. Okay, so does that make sense? It does, yes. So so we see that the angle theta, okay, maybe we can write that theta is the inverse tangent of omega squared r over g. Okay, and that's the answer. All right, so suggest how a value for theta can be determined experimentally. Okay, so we can, okay, how can we do this? Okay, so to calculate theta, we need omega, r, and g. So we can measure the period for 10 rotations and hence calculate omega. Omega is 2 pi over the period. Measure the radius. Measure the radius, maybe using a camera, I guess. Oops. Camera. Okay. And or a photograph, right? You can take a picture, right? So camera, picture. Okay. And find theta using the formula we just derived, omega squared times r over g. Beautiful. Question 16. A cyclotron at the Triumph National Laboratory in Canada produces beams of protons with energies from 20 MeVs up to 520 MeVs. A simplified diagram of a cyclotron is shown. Okay, there is a source of protons, AC supply, these high-speed proton beam. Okay, explain how the cyclotron accelerates the protons to follow the path shown. Personal story, I was once interviewed by Triumph for a position, for a postdoctoral position to work at the lab. Unfortunately, they didn't accept me. I expressed the interest to work there again in the future. They never replied. So I don't know. It would have been cool, but I guess c'est la vie. I mean, Canada, they do speak French, but not in Vancouver. Triumph is in Vancouver, Canada. So, and the French-speaking region is Quebec, which is on the other side of the country, in the east side. The west side is Vancouver. So, and I've been to Vancouver, by the way, for a conference when I was a postdoc at a different institution. So yeah, feels like ages ago. So okay, how does the cyclotron accelerate protons to follow the path shown? So there is a magnetic field. Let's start writing it. So there is a magnetic field pointing up. Okay. As the protons pass between the Ds, okay, they accelerate. So I guess the magnetic field points is perpendicular. Okay, let's write it. Okay, so that's B. Okay, it's perpendicular to the cyclotron. Okay. I don't know why I did that. So you get, I don't know why. Okay. Okay, perfect. So yeah, you have lines coming up. Okay. And how do we determine the how the protons? Okay, so the protons move this way. Okay, which means that if you use Fleming's left hand rule, let me think, we have to put our index finger pointing up, and then we have to put our middle finger in the direction of the velocity of the protons. So this direction, let me draw it in black. Okay, so that's V, and therefore the centripetal force is into the page, which makes sense, right? Because they circle around the disc, okay? So there is a magnetic field pointing up. As the protons pass between the Ds, so between the Ds means in this region, okay, where there is no magnetic field in between the Ds, okay? So as the protons pass between the Ds, they accelerate due to an AC voltage that has a constant frequency, okay, so that it always accelerates the protons. When I say always, I mean the protons will go first. They will travel, as we said, okay, let me think. So first it goes, the protons travel this way and then this way. In every direction, they encounter a negative polarity that accelerates them, okay? So that it always accelerates the protons inside the Ds. Inside the Ds, the magnetic field forces the protons to undergo circular motion with increasing radius due to their increased speed. Okay. So yeah, I think this is it. Is there anything else we can write here? So maybe we can write the equations. So I mean, since these past papers walkthroughs are also meant to teach you guys, so we can write that QVB. So inside this equation applies. So okay, QVB is mv squared over r. So v, one of the v's cancels. So the radius is equal to mv over qb, or p over eb, because the charge of a proton is just simply plus e. So as p increases, the radius increases. Okay, so as the velocity increases, the radius of the circular motion increases. And then to find this momentum of the protons, we can use that in between the Ds, we have E times the electric field, which is equal to V over D. So this is the electric field, is equal to 1/2 mv squared, or we can also write p squared over 2m. So the momentum of these protons is 2 times the mass of the proton times the electric charge of the proton, which is plus E, times the voltage, okay, which I write like that to distinguish from the velocity, over D, where D is the distance between the D's. So D is this distance. So this distance over there is D. All right. Part B. Part 1. Calculate the momentum in newtons times seconds of protons with a kinetic energy of 20 MeVs. You may ignore any relativistic effects. So E is P squared over 2m, and then m is the mass of the proton. So we can solve for P. P is the square root of 2 times the mass of a proton times its energy. So that's equal to the square root of 2 times 1.67 times 10 to the negative 27 times 20 MeVs, which is 1 MeV is 10 to the 6 EVs, and then 1 EV is 1.6 times 10 to the negative 19. Okay, and this is equal to 1.03 times 10 to the negative 19 newtons times seconds. Okay, now part 2. The Triumph cyclotron can produce beams of protons of different energies. This is done by extracting protons at different distances from the center of the cyclotron. Calculate the radius used to extract protons with a kinetic energy of 20 MeVs, and then they give you the magnetic flux density. So they mean that you see how the protons exit there, but they can exit there or in other directions, I guess. So for this we will use what we just derived over here. So the radius of curvature, we already proven, is equal to P over EB. So 1.03 times 10 to the negative 19 newtons times seconds over 1.6 times 10 to the negative 19 coulombs times 0.41 Teslas, right? Yes, so coulombs, Teslas, all these units cancel, and we end up with 1.57 meters. Okay, which is not much, okay? Part 3. Beams of protons can be used to probe the structure of matter. Determine whether the wavelength of 20 MeV protons is suitable for investigating nuclei of diameter 1.3 times 10 to the negative 14 meters. Okay, we can find the de Broglie wavelength. Okay, so the de Broglie wavelength of 20 MeV protons is given by h over p, and we calculated what the momentum of 20 MeV protons is, so we're going to use that. So 6.63 times 10 to the negative 34 over 103 times 10 to the negative 19. I'm being lazy with units. This gives you 6.44 times 10 to the negative 15 meters. Okay. Now the diameter is 1.3 times 10 to the negative 14 meters. Therefore, the radius of this nuclei is the diameter over 2, which is equal to 6.5 times 10 to the negative 15 meters, which matches the de Broglie wavelength of these protons. So the answer is yes. These protons are suitable to be used to probe nuclei of diameter 1.3 times 10 to the negative 14 meters. Moving on, question 17. The photograph shows a Van de Graaff generator used in a school. In the Van de Graaff generator, charge is transferred to a hollow metal dome which is insulated from the ground. The dome may be treated as a positively charged sphere with the charge distributed evenly on its outside surface. The electric field outside the sphere is the same as if all the charge were concentrated at the center of the sphere. The diagram shows the electric field for a positively charged conducting sphere. Suggests why there are no electric lines inside the sphere. inside the sphere, okay, the electric field is 0, so no lines, okay? This is a general property of conductors, because you can easily prove that if you have, for example, a positive charge there, okay, it creates an infinitesimally small charge there. It creates a field that will point like this, right? But in the diametrically opposite position, there will be another positive charge, which is gonna cancel pretty much the force from this charge, okay? So inside a conductor, there is no electric field, because all the electric fields cancel each other pretty much, because for each vector of electric field you have inside the conductor, there is, so for example, if we take this one, there is this one, equal and opposite, so they cancel each other, okay? Let's erase this, and let's move on. 2. Sketch a graph to show how the electric field strength varies with distance from the center of the sphere. Okay, so that's the radius of the sphere, and then the distance from the center. So inside the sphere, the electric field is 0. We can draw a line there at 0, and then outside we have this situation. Okay, and that's the answer. The capacitance of a conducting sphere, that's part B, question 1. The capacitance of a conducting sphere of radius r is given by C equals 4 pi epsilon naught r. The dome of the Van de Graaff generator behaves as a conducting sphere of radius 12 centimeters. The charge on the dome is 1.5 times 10 to the negative 6 coulombs. Calculate the potential difference between the dome and the Earth. So there are multiple steps in this. So first of all, we have to calculate, we can use that C is Q over the voltage, right? So the voltage is Q over, let me think, Q over C. So this is equal to Q over 4 pi epsilon naught R, okay? And we can immediately recognize that 1 over 4 pi epsilon naught is K. So K, Q over R is the voltage. So we can plug in numbers now, 8.99 times 10 to the 9 times the charge is 1.5 times 10 to the negative 6. This is what they told us. And the radius is 12 centimeters, so 0.12 meters. And the voltage ends up 112.4 kilovolts. Fun fact, one of President Trump's ancestors, maybe a great-grandfather or something like that, was involved, I think, in the Van der Graaff generator. Or maybe I'm mistaken. Let's check. So okay, President Trump. Okay, President Trump, relative Van de Graaff generator. Let's see, something like that. So let's see. Oops. So yeah, there he is, John Trump. Let's see. John Trump was an American electrical engineer and professor at MIT. He developed high voltage generators for cancer treatment, led radar deployment during World War II, and co-founded a particle accelerator manufacturer, one of the first startups funded through modern venture capital. He was the paternal uncle of President Donald Trump. So Trump earned his PhD in 1933 as Robert Van de Graaff's first student, okay? And this is the guy who invented the generator, okay? I think. He's best known for developing the Van de Graaff generator. Okay, so my intel is correct. So Unfortunately, President Trump is not sponsoring the channel. If President Trump is watching this, I urge him to invite me over or something like that. I don't know, or fund the channel. I don't know. But yeah, he had a relative who was into these things, and he was an MIT professor. I mean, respect. So, all right, let's move on. Part 2. The dome of the Van de Graaff generator is connected to Earth through a resistor of resistance R. Calculate the time taken for the Van de Graaff generator to lose 70% of its charge, and they give us the resistance. So, using the resistance, we can find the time constant. So, we have 9.1 times 10 to the 11, and then the capacitance is 0.12, which is the radius, times times k to the minus 1, right? I'm confused right now. So let me erase this. Okay, so r times 4 pi epsilon naught r. Okay, so this is equal to r times k to the minus 1 times r. Okay, now I'm happier. And now we have 9.1 times 10 to the 11 times 0.12, which is the radius, times 8.99 times 10 to the 9 to the minus 1. So this is 12.15 seconds. Okay, so now we can use the exponential decay law for the charge, for the loss of charge in the capacitor. So Q is Q naught e to the minus t over tau. So we need to lose 70%. Therefore, 30% will be remaining. So 0.3 is e to the minus t over tau. So we have that e to the t over tau is 3.33, and t is then ln of 3.33 times 12.15 seconds. Therefore, 14.6 seconds will pass. Okay. And question 18, I think, is the last one. So the photograph shows a demonstration electric motor. Okay. We have a coil of wire, magnets, an axle. Okay. A coil of wire is mounted on an axle so that it can rotate freely. Magnets are placed either side of the coil to provide a magnetic field. When there is a current in the coil rotates. The diagram represents the coil and magnets viewed from the end and from above. Okay, so I hope this makes sense. So this thing rotates inside the magnets pretty much, and from above you can see, like if we are standing up here, and we will see, let's see. So if we're standing on the top, at some point as this thing rotates, you will see something like a rectangle like that. But then this rectangle keeps rotating. So yeah, that's the idea. So A, the coil rotates clockwise as seen from the end, AB, in the diagram. Okay, explain the direction of the current in the coil. So this is what they mean. Clockwise means that the current flows this way. Okay. The coil rotates clockwise as seen from the end AB in the diagram. Okay. Explain the direction of the current. Okay. So, I mean, it will rotate this way. Therefore, the current that will be generated will try to oppose the reason that created it. So it's going to be that way. Okay. Oops, I don't know what happened. So let's, okay. Right. Part B. Calculate the maximum force on the side AC when the current in the coil is 0.29. So this is simple. We can use FBIL. F is BIL. So 0.074 is B, because they give us that. Okay. Then the current is 0.29, and then AC is this side, and they give us the length AC. So times 0.048, 0.048. So this is 1.03 times 10 to the negative 3 newtons. Okay, C. When the coil is rotating, the average current in the coil is less than the current in the coil if it is held stationary. This is because of the production of a back EMF. Explain how the back EMF is produced by the motion of the coil. So, first of all, let's write Ampere's law. The EMF is minus n, the number of coils, minus n delta phi over delta t, and delta phi is, or delta phi is delta b over a times delta t. And b is constant, so eventually we have minus nb delta a over delta t. So the change in area, in cross-sectional area, is what creates EMF. I will need a clean page to write the answer. So as the coil rotates, okay, it cuts through the lines of B. Okay, since this is a closed loop, okay, a current is produced which opposes the reason it created it. How does it do that? By rotating in the opposite direction, therefore it kind of tries to cancel the magnetic field. Okay. Second question, let me see, let me check my notes. Okay. So a wire of length L is moving at speed V through a magnetic field of magnetic flux density B as shown. Show that the EMF produced is given by BLV. So I guess as this thing moves, okay, so it moves in this direction, it kind of creates, it cuts through the lines of magnetic field, okay, and let's call this distance x. So let's use Ampere's law again. So E is minus d phi over dt. We drop the n, okay, we don't need it because this is not a coil, it's just a rod, right? So this is equal to minus d times b a over dt. B is constant, so it gets outside of that. So minus b dA over dt. And now what's the area? The area is simply L times X, right? That's why I made this rectangle. So the area is L times X, okay? The area it cuts through, right? So minus B times d of L times X over dt, but L is a constant, so minus B L dx over dt. But what's dx over dt? It's the speed, right? So minus BVL, and we can drop, I guess, the minus sign, because the minus sign only has to deal with Lenz's law and it's not needed here. So BLV, we proved it. Okay. Now 3, we go back to, I guess, let's see. The coil of the motor rotates at 9 rotations per second. Calculate the maximum EMF produced across the side AC of the coil. And they give you the width AB of coil. Okay, so I guess they prompt us to use this formula we just proved. Okay. Okay, so let's do that. So E is BLV, and by L we need the length of the side AC times V, but V is omega times R. Okay, so omega is 2 pi F, and then R is the length of the side AB over 2. Okay, so these two cancels. So E is B LAC, LAB, and then pi, and then F. And if we plug in the numbers, we find 2.41 millivolts. Okay, per turn. Okay, since we have 32 turns, okay, the final EMF is 32 times 2.41 millivolts, so that's 0.077 millivolts. Sorry, volts. All right, that's the answer. Part 4, the current in the coil varies as the coil rotates because the back EMF is not constant. Suggest why the back EMF is not constant. So the reason is that the coil, I mean, if you go back to this arrangement and see it closely, the coil at some points it exits the two magnets, so it's outside the field. Okay, so this is what I will write. This is what we will write. So the coil is outside the magnets for part of the motion, so the flux varies. And that's the answer. The average current in the coil can be measured with an ammeter. Suggest a method for measuring how the current varies over time. So let's see. Can measure with an ammeter. Suggest a method for measuring how the current varies over time. I guess you can use a data logger. Okay. And that's the answer. This was January 2018 paper. It's from the old spec, but I hope you guys find it useful. All the questions can appear in the modern spec. So thank you guys for watching. Please like and subscribe. And hope I will keep making these videos. So see you guys.